Bueno, hola, ¿qué tal? Muy buenas tardes a todos. Muchas gracias por estar hoy aquí en este coloquio especial que tenemos. Hoy tenemos de invitado al doctor Enrico Ramírez Luis. Él es mexicano, estudió física en la UNAM y se doctoró en la Universidad de Cambridge. Fue becario John Bacall del Instituto de Estudios Avanzados en Princeton antes de incorporarse como profesor o como investigador a la Universidad de California en Santa Cruz, donde es catedrático de astrofísica y astronomía y ocupa la cátedra presidencial Vera Rubin. Su investigación se centra principalmente en el universo violento, con énfasis en las explosiones estelares, la astrofísica de transitorios, las fuentes de ondas gravitacionales y los fenómenos de acreción. Está especialmente interesado en comprender los procesos físicos que rigen la acreción sobre objetos relativistas, como agujeros negros y estrellas de neutrones. Desde su incorporación al cuerpo docente de la Universidad de California en Santa Cruz en 2007, el doctor Enrico Ramírez Ruiz ha obtenido diversos galardones por su investigación, entre ellos la beca Packard, el premio NSF Career, la beca Radcliffe de Harvard, la cátedra Niels Bohr de la Fundación Nacional Danesa de Investigación, el premio presidencial a la excelencia en la tutoría de Ciencias Matemáticas e Ingeniería, el premio Mid-Career Head de la American Astronomical Society y el premio Bullshit y la medalla Dwight Nicholson de la Sociedad Americana de Física. Es miembro de la Sociedad Americana de Física y de la Academia Mexicana de Ciencias y la Academia Americana de Artes y Ciencias. Enrico, muchas gracias, bienvenido.
Gracias.
Y adelante.
Muchas gracias por la invitación, es un placer estar aquí. Como ya soy un pocho de lo peor, voy a dar la charla en inglés. Pero sí, muchas gracias, voy a estar aquí toda la semana por si quieren platicar conmigo, yo encantado. Okay, so I'm going to talk about new frontiers in transient astrophysics, and in particular, what can we learn through the counterparts of gravitational wave sources. And this is work that I have done in collaboration with a lot of amazing students and postdocs, and William Lee, who, as you know, we've been collaborating for a long time on this subject. So, you know, this event really drastically changed the landscape of astronomy, in which for the first time in the history of astronomy, we detected both the gravitational wave signal and then the electromagnetic wave signal. And we did it both in gamma rays and in optical. And in particular, I'm going to give you some insights to the optical light. And I want to kind of guide you through what we have learned and sort of the open questions that we have in the field. So, you know, this event was incredibly important. We were able to have an independent measurement of the speed of gravity. We were able to measure the Hubble constant. As you know, gravitational waves, the amplitude of the gravitational waves tells you the distance directly, particularly if you know the total mass of the system. We know that these objects, when they merge, they produce these highly relativistic outflows. And we also have really stringent constraints on the physics of neutron stars and dense nuclear matter. But what I'm going to tell you a little bit about is evidence for the creation of heavy elements via neutron capture. And I'm going to hopefully give you a pedagogical introduction to the hour process. But, you know, there's many, many open questions that we're tackling. We, of course, have only detected one event. So, you know, there's still significant amount of debate as to what caused the electromagnetic emissions in this system. Did the neutron stars merge? The neutron stars merger produce heavy elements? And are the source of all heavy hour process elements? I'll tell you a little bit about that. And a really open question is, what happened to this remnant after it merged? Did it collapse to a black hole, or it stay as a supermassive neutron star? And I'm going to guide you as to what we're going to see next, and kind of tell you how incredibly challenging it's been to actually detect another source. So it's been now almost 7 years since the detection. So I'll tell you a little bit about, do neutron star mergers produce heavy elements, and are they the source of all heavy hour process elements? Okay, so I'm going to spend a little bit of time in this graph here. This is from Chris Needham review. So what I show here is the proton number on the y-axis versus the neutron number. As you know, elements that have the same number of neutrons and protons lived here in the n equals z line. And you clearly see that once you go above the iron peak, the vast majority of elements that are stable, which are these black elements, have a significant fraction of neutrons. They have many more neutrons than protons, and that's going to be incredibly important. Now, the vast majority of elements above the iron peak are made by neutron capture. So when you capture a neutron, you become unstable, radioactively unstable, and you beta decay, okay? So the S process means slow, so that means that the capture of neutrons is slow compared to the beta decay. So that means that you capture a neutron, and then you beta decay, you capture another neutron, and you beta decay. And the way that you move is in this plane is you capture a neutron, you beta decay. So as you're making, S process, you're basically moving along these isotopes to the stable nuclei in what we call the beta value of equilibrium. So all of the slow process basically made elements, very close to equilibrium. Those are the stable nuclei. Now, another important thing, this is the beta decay timescale, how long it takes after you capture a neutron to beta decay. So it tells you the stability of those nuclei. So if I take a stable nuclei and I move downwards, what you see is that I move further and further away from stability. The lifetime of those nuclei is very, very short, okay? So that's going to be an essential, important component of the story. Now, this shows a characteristic R process pathway. So what is the R process? Is the rapid capture of neutrons. That means that you have to capture neutrons faster than you beta decay. This is for energies of about a few gigaelectron volts, separation energies. And if you want to make the R process, you have to basically move in nuclei that are very, very far from equilibrium. Now, in fact, nuclear physicists immediately realized, they looked at the pathway properties that you need. Oops, sorry. They looked at the pathways that you need, and they said, well, what is the characteristic time scale for the beta decay? So if you look at here, that's about 10 to the minus 2 seconds, so about tens of milliseconds. And then if you ask, okay, what object in the universe has dynamical time scales of the order of about milliseconds? The only answer is a neutron-star. So even, almost a decade ago, people realized that this R process capture has to be either when a neutron star is born or when two neutron stars merge. And of course, at that particular instance, you get a huge flux of neutrons. Now, I'm going to try to give you some insight as to the abundance pattern in the R process. And to do this, you have to think about the structure of nuclei, and in particular, these closed neutron shells. So these closed neutron shells is where nuclei are actually stable, and they don't actually want to capture nuclei. So what's going to happen? I'm going to show you in a second what happens in these magic numbers. And in fact, if you look at the abundance pattern of the sun, and you say, where are the peaks? The peaks basically correlate with nuclear stability. And why is that? So let me give you a feeling of this. So this is from the Clayton textbook, and it shows the neutron capture cross-section in the S process pathway. The first thing that you notice is the odd mass numbers tend to have higher cross-sections than even nuclei. So you see the variations in capture. And in fact, if you look at the solar abundance pattern, you can actually see that the abundance actually varies between even and odd nuclei. And that's basically correlated with nuclear stability. Now, the thing that I want you to focus on is how this is proton closed shells, but in the neutron closed shells, you can see a substantial lowering of the cross-section. What does that mean? That if you're a nuclei and you're stable, you don't want to capture neutrons. No? Why? Because you're incredibly happy being stable. So the way that I think about this is, imagine that you have a flow of neutrons, and you arrive to these magic numbers, and these magic numbers don't want to capture neutrons, the neutrons start to pile up. So they're sort of caustics on the flow. Now imagine that you have a highway with neutrons, and in these magic numbers, there's like a car accident, and then the neutrons pile up, and then you get an abundance peak. So as a result, abundance anti-correlate with neutron capture cross-sections, okay? And that's in fact why you get a peak. Now I'm gonna give you some insight as to the 3 primordial peaks after the iron peak. So for the S process, if I'm moving close to stability, I get this magic number and I get my first peak. I continue to basically capture neutrons. I get my second peak. I increase the capture rate, and then I get my third peak. So for example, if you look at in the abundance pattern, when you see the first peak, you clearly see, oh, that correlates to a magic number. The second peak correlates to the next magic number, the third peak. So these 3 peaks correlate really beautifully with closed neutron shells. But for, if you actually looked at what happens in the R process, so in the R process, you're far from equilibrium. So you capture here and you arrive to the first peak and you stagnate. So you get a peak, a second peak here, and a third peak here. But you're basically far from stability, so then you have to beta decay. So then this peak, when you decay, moves to the left, the second peak moves to the left, and the third peak moves to the left. So that means that when you look at them in an abundance pattern, they don't correlate with a neutron closed shell, because of course the neutron closed shell was a neutron closed shell when they were captured, but because they were far from stability, by the time you decay, those neutrons are then protons. Does that make sense? So this kind of nicely explains these, basically the abundance pattern of heavy elements, where you have the first peak here of the S process, the second peak, and the third peak. And what do you see when you look at the R process? That the R process first peak is shift to the left, the second peak is shift to the left, and the third peak is shift to the left. So they're happening at lower mass numbers, okay? Now, in general, if you see an element, the element can actually be made both by capture of neutrons slowly or captures by neutrons rapidly. So for example, if you look at lead is about 80% S process and 20% R process. If you look at my favorite peak, which is the third peak of the R process, which has gold, platinum, that one is primarily an R process. So precious elements can only be formed through the R process capture. Now, europium is highlighted here, and europium is highlighted here because it has an oscillation strength that is actually fairly deep. And this is the element that we use in stars when we looked at an absorption feature to say, oh, there is basically R process elements in that particular star. And these actually, you can challenge me later, but we don't really understand why there's a peak in between the second and third peak. Yeah? Some people relate that to nuclear structure. Some people relate that to the fragments as you capture basically piling up at these rare earth peak, but it's an open question, okay? So in neutron star mergers, what I'm gonna show you is that you need very, very high density of neutrons, which you have, and you need to eject that material. So ejection happens when 2 neutron stars merge in the tidal tails. I'll show you a movie of that. This is where the material that basically expands in the outer Lagrangian points, it's able to escape above the escape velocity. When the 2 objects touch, there's also high entropy that is generated, and some material is actually ejected in the pole. People call that the squeeze polar ejecta. But then if the merger remnant is able to collapse to a black hole and you form an accretion disk, you have a lot of basically winds from the accretion disk in which we actually think that you can make the R process. So there's a huge amount of discussion as to which of these are the majority or the most important source. Now, In the discussion that I'm going to tell you a little bit about, this electron fraction, which is really the neutron to proton ratio in the absence of pairs, is incredibly important. So in the disk queen ejecta, we have YE that it's about 0.1. So that means that you have 10 neutrons for about every proton. So the material is incredibly neutron rich. In some of these polar squeeze ejecta, the material is not as neutron rich. And I'll tell you a little bit about the challenges of doing that. So this is a very, very old simulation that I did in very close collaboration with Stefan Rosgo for my PhD. You have two neutron stars, identical neutron stars. So the system is symmetric. You get mass spreading in the outer Lagrangian points. The steepness of the interaction potentials basically lead to the objects become dynamically unstable. And what we're going to do together is we're going to follow the trajectories of these tails. So about 1% of a solar mass expands, gets above the escape velocity, and leaves the system. Yeah, and this is the tidal tail ejection. So what we're gonna basically follow these tidal tails and try to understand how the hour process is made in the tidal tails. Okay, so these should be familiar to you. It's very similar to the one that we saw. So we have protons in this direction, neutrons in this direction. And what I'm showing you here is the initial conditions. So let's go through some important numbers. I don't know if you can see them, but this is the time. I'm going to show you the temperature, which is in red, the density, and the heating rate, which are these three components. These are as a function of time. We're currently early on in the simulation, about 3.2 milliseconds. And the thing that you should notice is that in nuclear statistical equilibrium, so that means that as soon as the tails want to expand, you have a lot of heavy nuclei already and tons of neutrons. Yeah, so these are basically the abundance pattern in nuclear statistical equilibrium of the tails as they start to basically expand. And this is incredibly important because when you're incredibly neutron rich, the neutron richness of this material, it's shown here, it's about 0.1. When the material is so neutron rich, in nuclear statistical equilibrium, you already have the nuclei and you have the neutrons. So you have the nuclei that are going to capture the neutrons. You have both the projectiles and the targets, which is actually not easy to do, as you increase as the material becomes less neutron rich, that becomes more difficult to do. And I'll show you some examples of that. So I'm going to play you in a movie, and I'm going to show you how the neutron capture takes place. This is a movie made by Luke Roberts, who was a grad student working with me. And this is an hour process network that includes neutron captures, photodissociations, alpha and beta decay, and fission reactions. And it doesn't show. Oh, maybe it's frozen, I don't know why. So you're supposed to see a lot of the capture going up to higher and higher. It just go frozen. So it went all the way up and then start beta decay. And what you saw is the first peak, second peak, and third peak, the abundance pattern, and then the decay as a function of time. I'll run it again. It's something, I think it's a memory because I have too many things open. A ver, ahí va. No prende. Se salta nada más. Now, something that is incredibly important is that after you capture these elements and they start beta decay, you can see the heating rate continues. Yeah. So if you imagine this tail is expanding and it's going to be cooling as it expands, but these nuclear reactions, these basically radioactive decays, keep the material hot. And the reason why we see an electromagnetic signal, particularly in the optical and the infrared, is basically because it's powered by that radioactivity as these nuclei go back to stability. And once you go back to stability, you have the first peak, second peak, and third peak of the abundance ratio. So that's basically how it works. And we follow the evolution here to about 32 years of expansion. But in reality, as you will see, the radioactivity is really, really important at the weeks time scale. Should we try again? I don't know why the first. Yeah, it halts. Now, when the material, I will show you some trajectories. When the material is neutron-rich, you don't have these two peaks, so it's actually very difficult to make the R process. So these, it jumped from milliseconds to seconds. So we miss this initial decay. So the temperature basically decreases, the density decreases very drastically because you're expanding very close to the speed of light very quickly. Okay. So I'm going to give you some idea of how much R process you make. Almost the entirety of the ejecta, which is a fraction of a solar mass, is all R process. And I'll do it in my favorite element, which is gold. So one of these elements produces about a Jupiter mass of gold. So that's a lot of gold. Gold is about a few % of the total R process mass. And then if that's not impressive enough, this is about the gold stored in about millions of stars. So these events are rare, but produce so much material that you can actually supply a lot of stars with our process. And that's going to become incredibly important to the story that I'm going to tell you about how we owe these elements, the ability to live on Earth. But I'll talk about that at the end of the talk. Okay, so broadly speaking, this is the way that we think about it. There's lots of open questions about how you get two objects close enough for them to merge in less than the Hubble time. So these two objects, either a black hole and a neutron star or two neutron stars, are going around radiating gravitational waves. The gravitational waves carry both energy and angular momentum. The system starts basically getting closer and closer until they become dynamically unstable, but that lasts, the order of giga-years. Then when these two objects are very, very close, you get these dynamical ejection. In this particular case, this is the debris. These last a few milliseconds. You produce these R process elements. Remember that in order to produce them, the capture has to be very quickly, so it has to happen in less than hundreds of milliseconds. And then, as this material expands, nuclear heating is taking place, and it doesn't allow the material to cool. And then what you have to do is you have to wait a few days for the material to become optically thin, and the photons can escape. And it's at that particular time where we see the electromagnetic wave signature peaking. Yeah? And for the masses that we calculated, it takes between a few days to a week for the light curve to peak. Okay? And by that time, the material has reached size scales of a few AU, which you can also measure. Now, something that is incredibly important was to try to understand the nature of that radioactive decay. When we model supernova light curves, we're really guided by this beautiful way of thinking about it, which was introduced by the Arnett model. So you can think about your internal energy. Adiabatic cooling, that is basically auto-expansion. As you expand, the internal energy decreases. As photons leak out, the internal energy decreases because they're taking away some of that energy. This is the diffusion timescale, the characteristic diffusion timescale. And then all of the, both of these terms are taking energy away from the system. You need to heat it up. And this is the heating up that comes from radioactivity. And what I show here was one of the first calculations that we did with Luke Roberts in collaboration with William, in which we tried to really understand what is the decay, what is the shape of the decay. And in fact, Lee and Paczynski in '98, without actually doing any calculations, they say, oh, the decay has to be a power law. Why? Because there's so many nuclei that are decaying at a particular time that we think that naturally is going to give you a power law. And that's exactly what we saw. It's not exactly a power law, but it's well fitted by a power law. And what I'm showing here is the contribution of one single nuclei to the decay. So at a particular time, there's so many nuclei that are contributing to the heating rate. And as you know, in any statistical process, you tend to get a power law. So it was really important to get the shape of this power law, and I'll tell you a little bit about why. Why? Because we expect the bolometric luminosity, that means that the total amount of energy radiated, to follow the heating rate. Now, here I show a model, a type 1a model. Type 1as are actually powered by the radioactive decay of nickel-56 into cobalt, and then cobalt into iron. And the characteristic timescales are 9 days to hundreds of days. And this is the heating rate. So this is the heating rate, and this is the light curve. So the light curve, you're in the optically thick regime, you're expanding, you start becoming optically thin, you get a peak, and then you follow basically the heating rate very effectively. So a prediction that we made is that these models have to follow the heating rate predicted by our process radioactive decay. And these models were named kilonova models by Elliott Quarter here because they're 1,000 times brighter than a nova. So a macronova is, it's about like a 1A, and a kilonova is the scale. And you can see, one of the big difference is the amount of mass. In a type 1A, you're ejecting, order of a solar mass, but here you're basically only a percent of a solar mass. So the energy generation rate per unit mass is more or less similar, although for kilonova it's a little bit smaller, but the total amount is much smaller, and therefore your luminosity is weaker. So that's why these are very, very difficult to find. Okay, so the first prediction is if these things are, if our process was made in real time, in the light curve, when you plot the bolometric luminosity, you should see the power law decay from radioactivity expected from these models. Now, the second complication is what is the atomic structure of these elements? Why? Because the opacity, the optical depth through this material depends on the properties of these nuclei. And what I can tell you is that a significant fraction, and this is really transformative work done by Dan Kaysen, what he realized is that between the second and third peak of the R process, there are all these lanthanidines and actinides. And these nuclei are F-shell nuclei. What does that mean? That they have a very large number of possibilities in which you can arrange the valence electrons, and therefore you expect them to have a very large number of atomic line features. Let me show you this. Okay, so this is the atomic structure of something like iron versus, F-shell nuclei here. And you can see, while iron has a lot of lines, something like 300,000, these nuclei have about an order of magnitude more lines. So that means that the material is going to be incredibly optically thick. The photons are going to try to escape, and they're going to find these ocean of lines that are going to be basically absorbing those photons. And the photons are actually not going to be able to escape, not in the optical, but way in the infrared. So that was another prediction. And you can see here when you plot the opacity. So these are, now, something to know is that if you ask an atomic physicist to give you a line list of F-shell nuclei with all the energies and all the oscillation strengths, they cannot do that. So that is actually calculated statistically. So these opacities are calculated like, they're taking a lanthanide and F-shell, and you can see the opacity is very, very large, and it continues to be incredibly large. What if you have a D-shell like iron, the opacity decreases much faster. Yeah. So one of the predictions was if we made heavy R process, which is anywhere between the second and third peak, you will basically not be bright in the optical, but you will be in the infrared. So that was a really beautiful prediction. Oops, I don't know why. That's leftovers. So yeah, the lanthanide basically live here between the second and third peak. Okay, so what I show here is, radiative transport calculations, assuming what fraction of these lanthanides you have in the ejecta. So if you have very little, so this is what you will expect for iron, you will have transient that it's incredibly bright in the optical. And as I increase the lanthanide fraction here, you become basically redder and redder in spectra. Yeah? More or less, the fraction of lanthanides that you have with an R process pathway is close to 10 to the minus 1. So that means that the standard R process elements have a lot of these very, very complex atoms that basically prevent you from being very bright in the optical. And that's, of course, very bad news, because an infrared telescope, if nu of nu is flat, is about 100 times less sensitive than an optical telescope. Yeah, so this is also what makes it difficult to find these events. Now, imagine that you have these millions of lines, and these lines are moving at a fraction of the speed of light. The lines are actually incredibly broadened. So this is basically how the spectrum, so this is really beautiful because it tells you that you can actually measure the speed of the ejecta just by looking at the broadening of these features. And these are line features. They're not specific lines. They may be few elements that are at that particular wavelength contributing, but they're really an agglomerate of lots of lines. And you see these very, very sharp features. So as you go from 3% of the speed of light to 30% of the speed of light, these features just become incredibly broad. So that's another important aspect that we have, that we can actually measure the escape velocity just looking at the spectrum. Okay, so I just wanted to summarize what we learned from this event. So this was August 17, 2017, almost now past 7-year anniversary. We saw the gravitational wave signal. The objects are coming together. They're coming progressively together until they're about to become dynamically unstable. And by the time these two objects merge, the frequency is so high that LIGO cannot see it. Yeah, so we did not see the two objects touching, we didn't see the object merging, and ultimately collapsing into a black hole. So the new gravitational wave detectors are going to have increased sensitivity at high frequencies, so you actually can see the merger and the collapse. Remember, we see the merger and the collapse with two black holes because the black holes are more massive. That means that they're lower frequency, so they're very close to the peak. And if you haven't seen the gravitational wave signal, they're beautiful because the two objects merge, and then the final black hole even starts ringing down until it gets back to equilibrium. So one of the hopes of the new detectors is to actually see two neutron stars collapsing into a black hole and seeing the birth of the black hole. I was lucky to be part of the team that found the electromagnetic wave signal for the first time. We are the 1 meter 2 hemisphere collaboration. We have 1 meter telescope in the north, 1 meter telescope in the south. As you know, gravitational waves don't discriminate between north and south, so you have to expect both. And if you're interested later, I can tell you the story of the discovery, which is actually quite interesting. So a lot of that was led by my colleague, Ryan Foley, and I'm incredibly proud to be the oldest member of the group. And some of you may know Ariadna Murgia-Bertier, who was an undergraduate here and did her PhD at Santa Cruz. Okay, so this is what we saw. We saw the light being very blue early on, and then very red. So we were excited. We were not expecting this to be so blue early on, but we were excited to see it become so red, because that was the expectation. Remember that if there were so many R process elements, these things were going to basically be very bright in the infrared. So the first thing that we notice is when you do the bolometric corrections, which are not easy, especially at late times, you actually show that the entire bolometric light curve follows the heating rate very accurately, and that allows you to measure a minimum mass. You can say how much mass of radioactivity material I need to basically explain the light curve. And the answer is about 0.02 solar masses, so 2% of a solar mass. Now, we know that not all of that radioactivity is going to turn into light. There's some efficiency, so we calculated that the mass is about 3 times higher. So the assumed LIGO rate, of course, with only one event, is about 25 mergers per mega year. Yeah, so that's about a rate of 10 to the minus 5 events per year per galaxy. Yeah, so that means that you have to wait 100,000 years to have one of these in our own Milky Way. Yeah, and for comparison, a supernova is once every 100 years. So these things are 1,000 times less likely, but they produce a lot of mass. So as I said, the total mass that we predict is about 0.06. And if you multiply the rate by the total mass, you said that if all the events were the same, you will have produced about 10,000 solar masses of our process in the Milky Way. And remember, the total stellar mass of the Milky Way, order of magnitude, is about 10 to the 11. The R process fraction in the sun is 10 to the minus 7, so 10 to the 11 multiplied by 10 to the minus 7, you get about 10 to the 4 solar masses. Yeah? So you can actually supply with our process all the stars in the Milky Way. And of course, that is an over-prediction because not every star is like the sun. No, they have, a fraction of them have lower metallicity. So these seem like a viable model to explain all the R process. Now, if I show you, so these are the predictions made in advance of the observations, these red components, and what you can see is that the model is accurately predicted if we have 2 components. We have a blue component where we think only material from the first peak were made, and then a red component when material from the second and third peak was made. And we provide a relatively good explanation to the data. So this is the model that we came up with. The idea is that 2 objects are coming together. They produce this squeeze ejecta, so material is basically thrown in the poles. That material is neutron rich, so it's blue, and then that's followed by the collapse of the 2 objects into a black hole with an accretion disk, and then the accretion disk producing the red ejecta. Well, I hope this works. This is supposed to be a movie. Oh, there we go. So you see the blue component and the red component. And there's still a lot of debate as to whether it was actually radioactively powered or it's thermal, but the red component, fit our models, very well, and the spectrum model. Okay, so we believe that we had evidence for the cosmic creation of heavy elements. Why? Because the decay was what we predicted, and that the spectrum also showed that they had to be elements between the second and third peak. And if you know stellar abundances, you know that the R process pattern is incredibly robust, particularly from the second and third peak, which gives credence to this idea that neutron stars could in principle supply all stars in the Milky Way or the universe with our process. So the neutron stars merge, produce heavy elements. There's still a little bit of debate. And what I'm going to show you is that particularly, so in these tidal tails, the material basically expanded and was not irradiated by the neutrinos. When these 2 objects come together, the neutrino luminosities are so high that, in fact, the weak interactions, the positron and electron capture change the composition of the material and drive you to be more, less neutron rich. So these are the electroweak interactions, and as you can see, in this particular case, the emissivity of the neutrinos is very, very large, and when material is irradiated by neutrinos, the YE, which is this neutron fraction, goes close to 0.5. So that is a problem that it's currently unsolved, that you have to do radiation transport calculations with neutrinos to really understand the abundance of these elements. I'm going to show you here just the snapshots. Remember, this was actually the part of the movie that we missed. This was the initial very quick capture rate where the material is very neutron-rich, but at the same time, when the material is less neutron-rich, you actually don't get to the second peak. You only make first peak elements. So this is sort of the open discussions in the field. Can you make light process if the material is not very neutron-rich? Then you may be able to get actually, so you get the first peak. You can get a little bit of second peak if the material is slightly more neutron-rich, but when the material is highly neutron-rich, you get basically the entire abundance pattern. There's still a significant amount of debate. I would say that if you look at abundance patterns in stars, the second and third peak are incredibly robust. So whatever mechanism we make, it has to converge to that abundance peak no matter what. So I actually think that the models are not sophisticated enough. But there are some stars that are weird. So let me show you. So 1 out of 10,000 stars with high resolution spectroscopy. So this is, for example, a standard R process pathway of the sun, which is also very similar to this Needham star. And you can see the Honda star, which is called, only had basically light elements. So it had primarily a very, very large first peak, but then a very, very weak second peak and no third peak. Yeah, so people are debating, can these have been enriched by an event that was not as neutron-rich as others? So, but we only have this sort of high-resolution spectroscopy for about 10,000 stars. But you know that the vast majority of them, the abundance peak is actually very robust. Okay, there's, just briefly, we're detecting a lot of neutron stars with black holes in gravitational waves, and the question is, can they actually give you an electromagnetic signature? One of the issues that it's illustrated here, this is basically the spin of the black hole and the mass of the black hole in relationship to the neutron star. So what's happening? Well, if the black hole is spinning, the event horizon basically shrinks, yeah, which is important. In this region here, where it says no disk, that means that if the black hole is relatively massive, the neutron star falls inside the event horizon and gets disrupted inside the event horizon. So you don't expect to see any material. There's a transition region here once you start expecting to have a little bit of mass. And then, of course, if both the black hole is small and is fastly spinning, you can get a significant fraction of the mass. And these are sort of the distributions that we have from LIGO and M1 and M2. So you can see here clearly this is likely to be a neutron star with a black hole, but the black hole is about 8 solar masses. In this particular case, it's a little bit more uncertain. Maybe the black hole is about 5 solar masses. So if I show you, for example, it's not. Yeah, so I think something happened to my slides. So in this particular case, the neutron star is actually disrupted outside the event horizon, and you can see you can form an accretion disk, you have a tidal tail. But the current constraints are, especially of the spin, are not well enough that we know, in this particular case, in GA 200115, we see, the black hole could be 2 solar masses or it could be 8 solar masses. And in its spin, we know it has to be below 0.8. So currently, you could have solutions where there's no mass ejection and solutions where there was potential some material. And we're detecting more of this because, of course, they're more massive. So the gravitational wave signal is more intense, so you can see them from further away. So this is just to illustrate, particularly for this event, 1908-14, kind of the heroic efforts that the community is doing. This is of the order of about 3,000 hours of observation for this event. And you can see most of our kilonova models are here, and these are all the upper limits. So it's, it's becoming really, really difficult to actually see the detection. And in this particular case, it's more likely to be 2 black holes, so we probably did not expect anything. But people still put a lot of effort into trying to get to really, really deep constraints. So, if you have a really red kilonova, it's very, very, very challenging to find these systems. You can see things, for example, the things that are bright is if there was a gamma ray burst on axis or off axis, those are the things that you can rule out. Why? Because if there's a significant amount of relativistic beaming, the luminosity is much higher. So these are sort of the models that one can rule out to, to a lot of depth, but not the thermal component. So the future is exciting. LIGO and Virgo are detecting a lot of these events with CAGRA, and I think we all are waiting to have a kilonova with JWST waiting to be triggered, because the spectrum that we were able to make will be amazing. Okay, I wanted to just close the talk into telling you why these elements are essential to life. Even if you don't care about gold, you don't care about platinum, there's 2 nuclei that you actually should really care about. And these are uranium and thorium. So what I'm showing you here is the radioactive heating in the solar system, and in reality, the radioactive heating of Earth. And you can see early on in the evolution of the Earth, you have aluminum-26 provide the vast majority of the heating. But then as a function of time, most of the most common radioactive elements decay very quickly. And at late times is really uranium and thorium and potassium-40. Now, because potassium-40 is not as heavy as uranium and thorium, what ends up happening is that uranium and thorium actually sink into the center, and we think that the vast majority of the heating rate on Earth is given by uranium and thorium. And those 2 are our process elements, okay? So I'm gonna tell you about what you should care. Now, I'm gonna give you, if you're interested, I'm happy to talk about this. We've been doing a lot of cosmological models to try to understand the distribution of our process within the Milky Way. But the message that I want you to have in your mind is, if you have core collapse supernova that produce, say, oxygen, they happen very, very commonly, and they produce little amount of mass of oxygen. Yeah. So if you think of a chocolate cookie, think of a chocolate cookie with a thin layer of chocolate that it's very, very thin and widely distributed. So chemical enrichment of supernova is very homogeneous. But if you think about our process elements through neutron-star mergers, it's like a chocolate chip cookie, where all the elements were basically concentrated. So that means that if you're a star early on in the history of the universe and you were formed here, you will have a lot of gold. But if you were formed here, you probably have little gold. So you see large variations, and that's exactly what we see in the observation. So this is, say, for example, for magnesium and europium. And if I show you exactly, these are just both halo stars and disk stars. In astronomy, we plot iron over hydrogen in log units. So the sun is in 0, 0, so this is where we lived. And this will be 1 part in 1,000 of the iron content of the sun. And then what you see, if you see magnesium, you see that there's basically small RMS fluctuations. But if you look at europium, there are very, very large fluctuations. So these stars were born very close to the chocolate chip cookie, and this one's very far away. And then turbulent mixing takes place, and it basically decreases this envelope as a function of time. Yeah, because material is basically mixing constantly in the universe. And the very important thing that I wanted to highlight is that even at solar metallicity, we believe that there's a factor of 3 in our process content. So the hypothesis is, imagine that you have 2 stars like our sun, that they're identical in their metal content, but one has 3 times more our process, and one has 3 times less our process. What will happen to the planet around them? Yeah, the Earth with more our process will be heated more efficiently, and the one with less significantly less. And what are the consequences of that? And the reason why we started looking into this is that what drives the convection motions on Earth are both the heating rate of uranium and thorium. And convection coupled with rotation gives you the dynamo and amplify the field. So the question is like, oh, are we going to expect some Earth-like planets not to have a magnetic field? And if they don't have a magnetic field, you don't want to live in their surfaces. So that's what we investigated. And the answer is, it's incredibly important. So this is from a paper led by Francis Nemo, a colleague of mine at UC Santa Cruz. And what we found, it says, well, if you have a lot of our process, and by a lot I mean a factor of 2, more our process, the convective motions are so vigorous that the alpha omega dynamo doesn't work. So that means that you will have more radioactive heating, you will have extreme volcanism, but there will be no magnetic field. So you will have an Earth-like planet without magnetic field. It seems, that we live in a special place, also in the terms of the content of europium, because we are actually kind of average between stars. And if you have less, the convective motions will be less intense, but rotation will couple well with those convective motions. You will have a magnetic field, but you likely will be geologically dead. So you won't have any volcanism. And the question is, if you believe that volcanism is really important to life, then you really need to have the right amount of our process material. So now, even if you didn't care about our process being the products of the most beautiful, high density, high temperature collisions, you still should care because we are here because of uranium and thorium. So just to summarize, we live in an era of gravitational wave astronomy. This is so far the only event that we were able to see both in gravitational waves and in light. There's a lot of exciting things about merger dynamics, but also about the type of nucleosynthesis that happens. And I briefly mentioned it, but there's a significant amount of work thinking about the importance of neutrinos in changing the composition. And even things like habitability are starting to become incredibly important. So if you know the Drake equation, there's an additional term on the Drake equation for habitability that tells you how much our process material you have. And I'll stop there. And yeah, muchas gracias.
Bueno, muchas gracias, Enrico. Vamos ahora con la sesión de preguntas. ¿Alguna pregunta aquí en la sala?
Okay, gracias, Enrico. When you describe our process in the mergers, you produce a lot of elements between the second and third peak.
Sí.
You never mentioned producing uranium and thorium, so where does it come from?
Vamos a ver la tabla periódica. ¿Lo vemos ahí? Estaba viendo ahí. Yeah, so uranio y torio son actinides que están precisamente entre el segundo y el tercer pico, ¿no? Entonces tienes que hacer el segundo y el tercer pico para hacer estos dos elementos, ¿no?
Me confundí. Yo pensé que era lantanide en el segundo.
No, ambos. Todos estos, todos los que están aquí, están entre el segundo y el tercer pico. Entonces son heavy R process nuclei.
But you had figures with Z numbers, and it just dropped to after 82.
Sí, pero tienes el pico. We can talk about it. It's the heavy peak in the end where you have uranium and thorium in the peak, and all of that is measured in stars, and it fits the abundance pattern very well. Creo que hasta la estrella esta de Sniden las tiene. Yeah. So, no llega tanto. Están por aquí. Yeah, and el patrón de abundancia es de aquí hasta donde está uranio y el torio, en las estrellas es muy robusto. Entonces tienes que hacerlos más bueno, sí necesitas que el material sea muy neutron rich, ¿no? Para que llegues a estos elementos.
Una otra pregunta aquí en la sala.
Te busco una figura con las observaciones de uranio y torio.
Hi, I apologize in advance for my, I don't know, ignorance on the topic, but it's my understanding that gravitational waves are detected by interferometers, and that there's some limit to the sensitivity that those can have. You mentioned during the talk that there was hope that we could someday detect neutron-star mergers, but that would require higher sensitivities. Would those instruments be possible to be built? Would it be possible to build those instruments here on Earth, or would those need to be sort of based on space?
Yeah, so we did detect, so this gravitational wave 170817 came from 2 neutron stars. What I was saying is that we didn't see, when the 2 neutron stars came together and merged and then collapsed, we didn't see that in the electromagnetic signature. But, so, the way that gravitational waves work is like your ears, So if you close your eyes, you're completely blind to this plane of symmetry. So LIGO had 2 detectors, yeah? So you can see, le dicen plátanos en el cielo, So those are uncertainties in this direction, yeah? Pero ¿qué pasó aquí? Se prendió un tercer detector en Italia, entonces ya tenías 3 oídos, y eso nos dio la certeza de encontrar la posición de este objeto con mucha más eficacia que antes, Y ahora hay 3 detectores, entonces eso te ayuda, aunque el tercer detector no es tan sensitivo. But you're right, so we have detected lots of black holes, but we cannot pinpoint them in the sky, and then this gravitational wave was one of the closest and brightest signals, and this is the one that we saw, the electromagnetic wave.
But could you do the same that you did with the to sort of pinpoint or sort of limit the region those black holes could be in?
Yeah.
Why hasn't it been done then?
Well, so the issue is, do you expect to see any light from 2 black holes merging? So most people think no. So if you think, for example, so people are trying to do cosmology this way, but it's going to take a long time. So if you ask in the error circle where the black holes are, how many galaxies there are are about 100,000 galaxies that could be associated with that black hole. But you don't know which one it is until you have electromagnetic waves. And people think that you can actually say, oh, I'm going to just do a statistical distribution and say, they have a probability distribution to be associated, and I get a redshift for those galaxies, and if I do that 1,000,000 times, I can get the Hubble constant. I don't think so. You really need the electromagnetic signatures, yeah, so that's why we can only do it.
Okay, thanks.
Yeah, I think, sí. Si tuviéramos 3 LIGOs de la misma eficacia, entonces el número de galaxias es como que 1,000, 10,000 galaxias. Entonces, aunque no tengas contrapartes electromagnéticas, pero si no las tienes, entonces todo el mundo, bueno, yo creo que no va a haber ninguna contraparte electromagnética si tienes 2 agujeros negros, porque no hay gas.
No veo manos levantadas en Zoom, entonces, si hay alguna otra pregunta aquí en la sala.
Gracias, Enrico. Hay una familia muy grande de ecuaciones de estado que describen a las estrellas de neutrones. ¿Se pueden usar estos cálculos para tratar de restringir esa familia de ecuaciones de estado?
Sí, bueno, aquí el experto está aquí enfrente, pero en general lo que sí vieron fueron deformaciones de las estrellas. O sea, si tienes la posibilidad de ver que estos 2 objetos se están acercando y se empiezan a deformar por efectos de marea. Y esas deformaciones, la amplitud de deformaciones te dice qué ecuaciones de estado son válidas, pero creo que todavía esas deformaciones no son lo suficientemente bien observadas o restringidas para poner cotas como muy estrictas. Realmente la mayoría vienen de medir el radio y la masa de la estrella, ¿no? Pero sí, en general, puedes decir que las oscilaciones, que no había muchísima masa de los objetos en las partes externas, pero de cierta manera pocas ecuaciones de estado esperábamos que tuvieran esa cantidad de masa. Pero en general sí, ¿no? Es precioso que la amplitud de esas oscilaciones se ve en la onda gravitacional. ¿Sí?
Pero entonces, todos estos cálculos del R process son independientes de la ecuación de estado.
No. Depende bastante de la ecuación de estado, pero como el material que estás eyectado es a densidades más bajas, la ecuación de estado no hace una diferencia tan amplia en la nucleosíntesis del material que eyectas. Realmente lo que va a importar más es el transporte de neutrinos, particularmente si es ópticamente grueso. Eso va a estar complicado. La masa de... Sí, para el colapso, por ejemplo, ¿no? O sea, cuando estos dos bichos que tenían una masa combinada de 3 masas solares, todo el mundo dice, bueno, pues retener esa masa o no con una ecuación de estado normal. La idea es probablemente no.
Ok. Aquí hay otra más y...
Gracias, profesor. Un poco siguiendo con esa pregunta, la densidad que alcanza el material, las colas que salen eyectadas, ¿es entonces como del orden de una densidad nuclear o es menor o es...?
Como 10 a la 12
gramos por
por
cúbico.
centímetro.
Ok, bueno, entonces...
Y de ahí caes muy rápido, ¿no?
Y la segunda pregunta era si se podría tratar de explicar la primera señal, la azul, que se notó usando, no sé, campos magnéticos de las estrellas de neutrones o algo por el estilo.
Sí, bueno, el argumento es que los campos magnéticos van a crecer un montón cuando estos objetos coalescan, ¿no? Porque vas a tener un montón de rotación diferencial. Puede ser que el material eyectado al principio es mucho más intenso si tienes campos magnéticos. Hay cálculos que muestran eso. Lo que pasa es que esos cálculos son complicados cuando las densidades son muy bajas porque la energía magnética es muy alta, ¿no? Entonces hay una disipación interna del código que no te lo permite. Pero sí, en realidad la gente también dice que puede ser una componente térmica de energía que se inyectó, se generó un choque, el choque se volvió ópticamente delgado y te dio un pico que es térmico, pero no tenemos un espectro. Entonces solo tenemos la curva de luz del pico azul. Pero bueno, ya ves, los teóricos se inventan un montón de avenidas para hacer ese pico. Pero la idea de campos magnéticos es muy importante y realmente son difíciles de calcular y poca gente está haciendo campos magnéticos, transporte de neutrinos y nucleosíntesis a la vez.
Ok, gracias.
Pero sí puede ser.
Hola, gracias por la charla. Las simulaciones que hacen son SPH.
Las muy viejas eran SPH. Sí.
Ok. ¿Y ahora qué utilizan para...?
En realidad ahora hacen códigos hidrodinámicos ya que le llamen moving mesh o fixed mesh, con full GR. Bueno, ahí está el experto aquí al lado. Full GR, time dependent GR,
Okay.
con el MHD.
Entonces, ¿cómo relacionan todos esos decaimientos en las colas para estos alfa y beta decaimientos? ¿Cómo los meten en el código como tal?
Sí, o sea, nadie ha hecho... Lo que la gente hace es toma estos códigos hidrodinámicos con toda la física que quieras y avientas material. Y entonces sigues las trayectorias termodinámicas de densidad, temperatura, ecuación de estado del material, cómo se evoluciona por esas trayectorias, y ahí haces la nucleosíntesis, ¿no? Porque hacer la nucleosíntesis al mismo tiempo que hacer la hidrodinámica es muy compleja, nadie lo ha hecho. De hecho, en general, si te fijas, por un segundo más o menos, la energía inyectada por estos decaimiento es constante como por el primer segundo. Entonces hay muchos argumentos que aunque vas, colapsas, te vuelves un agujero negro, las colas están ahí, durante ese tiempo digamos, el calentamiento radioactivo puede ser importante para la hidrodinámica, pero nadie lo ha hecho de manera consistente. Una vez que estas trayectorias son eyectadas, hacemos la nucleosíntesis de esa manera, ¿no? Y si estás lejos, ya los neutrinos no te afectan, entonces de cierta manera es bastante robusto, pero lo que tienes toda la razón es que tú no me puedes decir cuánta masa es eyectada y cuál es la nucleosíntesis hasta que pongas toda la física en detalle, y no la tenemos, ¿no?
¿Puedo comentar algo rapidito?
Sí.
Lo que se hace es justamente, o sea, mides la densidad de la estrella y con eso le asocias a un elemento, por ejemplo, la densidad del elemento. Lo que sí se hace hasta ahora es nada más resolver las ecuaciones de transporte para los neutrinos, y eso sí los puede resolver acoplados. Pero todavía a nivel de decaimiento es bastante difícil. Al menos en códigos relativistas es súper difícil, pero tienes esas dos componentes.
No veo manos levantadas en Zoom. ¿Hay alguna pregunta por ahí, la gente de Zoom? ¿No? ¿Una pregunta más aquí?
Comentas que estos eventos son bastante luminosos en neutrinos. ¿Se han observado en IceCube? Por ejemplo, ese evento de 2 estrellas de neutrones.
O sea, los neutrinos que tú produces, particularmente por estas interacciones, ¿cómo se dice? Electroweak. Electrodébiles. Te dan neutrinos de electrones y antineutrinos, ¿no? De electrones. Y esos son neutrinos térmicos. Son muy similares a los neutrinos que tú ves en una supernova. Pero recuerda que los neutrinos térmicos que hemos visto en una supernova fue cuando la supernova estaba muy cerca de nosotros y no hemos vuelto a verlos. Entonces, para ver los neutrinos térmicos de estos bichos va a ser muy, muy difícil. Tienes que buscar, por ejemplo, quizás los neutrinos que son hechos en el jet, que ya estás moviéndote relativista, donde las energías de los neutrinos son mucho más altas que o sea, estos neutrinos son de 5 a 10 megaelectronvolts, ¿no? Y tienen el espectro térmico, entonces son difíciles de ver. Yo creo que en nuestra vida nunca vamos a ver los neutrinos de uno de estos objetos, porque dijimos uno cada 10.000 años o 100.000 años. Y los detectores de neutrinos tienen que ver 10.000...
Como un teraelectronvolt.
Sí, como 10.000 galaxias cercanas, y la sensibilidad, bueno, quizás, no sé, quizás tienes que cubrir la Tierra completa para verlos, pero no sé.
Bueno, pues con esto terminamos. Le damos nuevamente
Gracias.
las gracias a Enrico por el coloquio de hoy. Muchísimas gracias a todos por su asistencia. Gracias.